Hello everyone, my name is Alex Dahl. I'm a mineral grinding specialist, and in today's video I want to talk about some of the sources of uncertainty associated with the Bond ball mill test. So I think most of you are familiar with the test, but very quickly, the test is performed in an apparatus consisting of a tumbling mill. It has dimensions that are specified, it has a particular geometry inside the mill that's specified. The test apparatus, the mill spins at a particular speed. The key thing is that the operator is going to be measuring the number of cycles that the mill turns. And then after a cycle, the mill stops, material is retrieved, material is weighed, new material is added back to replace finished material that's removed from the test charge, load the mill back up, turn it again. So basically it's a lock cycle test, standard apparatus, and it takes several hours to run one of these tests. The lab needs a little bit of auxiliary equipment. So you've got in this picture from ALS in Kamloops, we've got a sieve stack off on the right, which is just out of the picture here. There's a sieve shaker or rotap if you prefer, and you need a weigh scale. So you don't need a lot of really specialized equipment other than this ball mill apparatus and the sieve set. So the good news is that this test is arguably the most common ore hardness test in the world, and it is open technology. There's a lot of vendors who provide a Bond ball mill apparatus. There is no single vendor that controls this test. There is a guideline published by the Global Mining Guidelines Group, which was a collaboration of many people in the industry. Those procedures and guidelines are published, and anyone can perform the test if they have the apparatus. Now, the bad news associated with this is that there is no governing authority. So anyone who wants to run the test can run it, whether they run it correctly or incorrectly. If they want to run it wrong, they can very well do that. But there's a bigger issue here, that there are, even though the procedures are published, there are gaps in the procedure. And it's going to be up to you as the end user to build some quality control into your grindability testing program. So you as the source of the material, you as the source of the instructions for what to test, you need to be aware of some things to improve the quality of your grindability programs. One of the issues that I've actually been, one of my customers got caught out on this. A brand new mill from the equipment manufacturer, this is the laboratory apparatus, it's going to have a rough interior surface. The lab must wear down that interior surface and make it smooth before work index determinations of that apparatus become valid. So there's some published information on the internet that shows that the work index is about 10 to 12% higher when the mill is brand new prior to all of these surfaces being worn smooth. So you cannot just take an apparatus out of the box, install it in a lab, and start generating work index numbers. You've got to run it in with a period, running with like a silica sand charge. So here's the example from the Colorado School of Mines. This is some undergrad work. You can see in the photo the interior of the mill. There is like a little casting defect in there. That's the sort of thing that has to be worn smooth when you install that mill. So this mill needs to be run for 100, 200, some cycles with like an abrasive sand to wear that surface smooth. Another issue to be aware of is that the standard ball charge is actually not that standard. So in the guideline, it calls for 285 iron or steel balls. So right there, that should set something off. Iron and steel are not precisely the same thing. So the lab can correctly choose one or the other, and that will affect the results. In the guideline, there's quantities of balls of specific dimensions. The key thing most people pay attention to is the weight of the charge. Some of all the balls should weigh 20 kilograms and 125 grams. in the specification, it calls for a surface area on the charge, but that's almost impossible to measure. So generally people count the number of balls of the particular sizes and they weigh the total mass of the charge. Now, one of the vendors of the apparatus that sells ball charges, they actually generated a slightly different charge, which they claim is based on an equilibrium of what you would get with the bond standard charge, which is what comes out of the GMG guideline. And if you ran that and had an equilibrium where you're pulling out worn balls at a particular time and adding the fresh balls, they claim this slightly different group of balls is what you would end up with in equilibrium. And what this looks like in a tabular form is you've got a slight difference in the quantity of balls and the dimensions of the balls, where this equilibrium charge that BECO generates, they claim has more intermediate sized balls. It's got fewer of the very coarse balls, although they are slightly coarser at the top end, and slightly different arrangements of the finer end of the balls. So this is some more published work. This comes from K.F. Fletcher Thompson. They've got two different versions on the left here of the GMG charge, where you can, if you count the number of balls, those all fit the guideline. You look at the total mass of the balls, the 20.125 kilograms. Those are all correct, but you notice that it's possible to have slightly different weights in each of those size classes, and that's just due to the wear on the balls, right? How much do you allow a ball to wear down before you pull it out and replace it with a fresh ball? So in the green box, you've got the uncertainty just associated with using the one standard ball charge as things wear down. And for comparison, you can see the BECO charge on the right in the red box, and then there's some other standard charges that they encountered out in the wild. So the key message here, the ball charge isn't standard. How the labs decide to replace a worn ball is not necessarily standard. What goes on in the mill is that charge reaches some sort of an equilibrium ball size distribution. So the key thing for you as an end user is to realize that there is uncertainty in this ball charge, which means there is some uncertainty in your test result. So understand what your lab's quality control procedures are. Right? They will have some standard for when they pull balls out, how often they measure them. Ask what that is. And it's quite common in the programs that I run. I'll ask them right up front, go out and measure your balls right now. Tell me how many you've got. Tell me what the weights are in the different size classes. Tell me what the total weight is. So what you can do as an end user, you can build those sorts of quality control measures into your laboratory programs, whether it's an external lab or your internal labs. Also consider having an experienced person, right? I'm a consultant. This is what I do for a living, that oversees your laboratory program and can potentially catch some of these issues before you've run 100 samples that you've spent $1 million generating through the lab, only to find out that they didn't wear in their brand new ball mill properly. So how bad is this? Published information says that the repeatability of the test, which means you've got the same operator, the same laboratory, the same mill, the same ball charge, if you just run the same sample through it twice, you should get a result that's within about half a metric work index unit. So if you've got a value of 10 and you got a value of 10.3, those are effectively going to be the same result. That's the sort of variation you would expect up to, from 10 to about 10 and a half, 10 to 9 and a half. Reproducibility. This, there's a bunch of papers out there. Somewhere between 8% and 10% reproducibility is what you can expect. So that's going to a different lab. They will have slightly different ball charges. They will have slightly different apparatus. They will have different operators. So the implication is that your work index results, they have an uncertainty margin. So things like the third decimal place, those are not useful. Those are not real. Again, if you've got a value of 10 and you've got a value of 10 and a half, those are basically the same result, right? So I have no problem with seeing bond work index results to 1 decimal place, but don't do it to 3 decimal places. You're fooling yourself if you think the test has that level of accuracy. So what can you do to build quality control into your program? Okay, first of all, you know that the lab should have their own quality control. Ask what they've done. Ask for their procedures, and then just verify on a checklist that somebody has checked the box that says they've measured what the ball charge weights are, and ask for that sheet where they've actually verified what the ball charge is before your test start. In your program, add some redundancy by putting duplicate samples into the sample stream that's going to the lab. Right? This is very simple. You just take one of your samples, well, more than one, split it in half, put different sample numbers on those two, and send them into the lab. And when the results come back, the lab will think they're different samples, so they're going to come back with different work index numbers. And then you, in the post processing, can work out what the repeatability was, because you know that those two were actually the same sample. And it's actually a good practice to feed that back to the lab once you've done this check, so that, again, that helps them improve their practices. If you submit these duplicates without telling them that they're duplicates, and then after the fact you give them back and say, yeah, sample 3 and sample 14 were actually the same thing, and your values were within 0.1 work index units, that's excellent, right? That's the sort of repeatability you'd hope for in a program. Another thing you should build into your programs, especially for the bond ball mill test, is test the ore sensitivity to the P80 size. So on a small number of representative samples, the mythical representative sample, this would usually be on like a UGM composite or something like that, run duplicate samples at different closing sizes. So measure what the effect of the change in the P80 size is on the work index. And I've given an example here where the coarser the P80 size, the coarser the closing screen we run the test at, the higher the work index number is. So this is relatively common, but this is actually an ore characteristic that each ore can have its own shape of this curve. And part of what we want to see here is that there is a particular regression equation we expect these results to fit, and if they don't fit that, that's a hint that either you've got an ore that does something very unusual, or that there might be an issue in the lab test. So again, this is a way of building some redundancy into the program, as well as generating extra information. You're getting the P80 effect on work index, but you're also validating that the work index is that they're repeatedly hitting the expected amount of variation you should get with repeat tests. Another form of quality control that should be part of every test program, always collect a complementary test. So an example of a complementary test is the SMC test, which is a type of drop weight test. My particular favorite complementary test is the bond rod mill work index test. You can use SPI, you can use SAG design. There's a whole bunch of other tests you can use here. But the key is to observe what the ore hardness is in 2 dimensions. So in the chart here, I've got on the vertical the bond rod mill work index. On the horizontal is the bond ball mill work index. The triangles are the ore in question, and then all of these gray points in the background, that's my overall database. So with this, we can see that this ore has a response where its work index in rod milling is higher than the work index in ball milling. And there are some samples that are outliers. Okay, well, every program has a little bit of that. But overall, you can see that the triangle points are all clustered together and they form a trend. So that's a form of quality control, that if it's hard in the one metric, it's also hard in the other metric. And you want to test that as a complementary test to try and flag if something's gone haywire at the lab with your ball mill work index Alternatively, it could also be the rod mill work index. In this case, it's off. But in general, all of the points that are up in that nice cluster, you've got pretty good confidence that those are robust tests. And then you can start asking questions about these outliers. What happened there? Another approach we can use is to use a large quantity of low reliability tests that can generate a robust database. So what I was talking about before is improving the robustness of individual tests. You can also spam a whole bunch of low reliability tests and have signal arise out of the noise. So a highly noisy test, if you repeat it enough times, will generate a useful average number and a standard deviation number, but you're generating population statistics here. So you can use that as a way to characterize ore bodies using things like, again, this QQ plot you see behind in the figure. So these are, you can use abbreviated tests for this. So there are cheaper, like mini bond is one example. Modified ball mill work index is another example. Each individual determination of these tests is lower accuracy than the full test. So instead of being plus or minus half a work index unit, it might be plus or minus 2 work index units. So you've got bigger uncertainty bars on each individual determination that you've done. But you can do lots more of them for the same budget. So, in really round numbers, let's say we had an abbreviated test that has 1/10 the cost of the full test. You can run 10 tests for the price of one full test. You've got 3 sets of data, or 10 data points, which you can now do statistics with, rather than a single point that you can't do any statistics with. So this opposite approach to a high reliability bond ball mill test is abbreviated tests and lots of them. So here's an example of what I've done with using population statistics. So the QQ plot you see on the left here, the crosses are the original lab data, and it's plotted in a QQ plot. So you've got your probability axis is along the bottom, and the determination of the work index is on the vertical axis. And what I'm trying to do is tweak the inputs to the Monte Carlo model, which is what you see in red, so that it matches reasonably close to the blue crosses. So I'm trying to come up with a population in the Monte Carlo feed that matches the population we observed in the large work index program. And then on the right, you can see the Monte Carlo model results are saying that, of the 80% of, at an 80% probability, you're going to exceed the baseline of 160,000 ton a day for this design. So this is the sort of design work that you do with population statistics, which is going to be slightly different to what you would do if you just had raw work index numbers and you run them one at a time and one at a time and one at a time. Okay, so the bond ball mill work index test, or the bond ball mill grindability test, the strength of it is that it's a lock cycle test. So that makes it very robust, especially when you've got minerals that are mixtures, when you've got composite feeds. You might have a hard and a soft component in that feed. And by running the lock cycle test, you end up with an equilibrium where the soft material passes through the test faster than the hard material. And that replicates what we see in the lab, replicates what we see in the industrial plants. So that lock cycle aspect is crucial to getting a reliable bond ball mill, full bond ball mill test. Once you've got that established, what happens as you get to equilibrium in a full bond ball mill test, then you can calibrate these mini bond or modified ball mill tests that do not reach an equilibrium. That's one of the aspects of these modified tests. They don't reach an equilibrium. Another strength of the bond ball mill test is it is adjustable to a range of product sizes. So we touched on that already. So that's really useful because in the laboratory program, you can tune the program to give you a work index result that matches what you're going to get as a P80 in the industrial plant. You can tune the test in the laboratory to match your design. A strength of the test is there's no license fees, right? Any lab can run the test. They don't have to pay anybody. They don't have to worry about economic sanctions because they're in a country that is unfriendly with the licensing country. There's none of that. There's also a large worldwide database of results that you can use to benchmark and compare. So excellent test with all these strengths. The future of the test, I think this test is going to be relevant for decades. Now, having said that, there are some alternative apparatus that are appearing and that will eventually be able to be calibrated to provide work index numbers. And I think one of the things we're going to see in the industry in the near future is more use of statistics and a large number of these low reliability determinations by things other than a full bond ball mill test. Ideally, I would love to see a test that is done in the core yard, not in a distant laboratory, but as the core is being processed. So the geologists take a length of drill core, they do their logging on it, and then the drill core, perhaps it gets cut and half goes back in the box. The half that goes out for assay, prior to going out for assay, do a ore hardness measurement on it. That's what we're seeing here. This apparatus is not precisely what I'm describing. This is the min-praxis tester that generates statistics for geotechnical information and can estimate drop weight indices as it's doing the size reduction of core to make an assay sample. At the end of this test, they got a bag of material that then goes out to the assay lab. So this is a crusher that makes lab samples, but it also pulls out geotechnical information. And something like this could probably be calibrated to also give us work index information in the future. So I think that's the future. We're going to do less testing in the laboratory, more testing in the field. We're going to generate lots and lots and lots more data. And then we're going to start working more with statistics and less with individual tests. So with that, I will say thank you very much for your attention, and I look forward to speaking with you in the next video. Bye-bye.